This is Lesson 20 in our Calculus 2 series, Arc Length. In this lesson, we're going to learn how to find the length of a curve. Now, so far, we know how to find the length of linear segments, that is, the distance between 2 points. So recall, if we have points x1, y1 and x2, y2, the distance between those points is given by radical x2 minus x1 squared plus y2 minus y1 squared. And that comes from the Pythagorean theorem by making a right triangle here. Now, to find the length of a curve, we think about approximating the curve with linear segments and taking the distance of those linear segments and adding it up. And then we'll take the limit as the number of segments approaches infinity. So for example, to find the arc length of the red curve, we approximate that curve by linear segments and add up those distances. Then we'll take the limit as n goes to infinity, where n is the number of segments. So consider f of x having f prime of x continuous on the closed interval ab. To find the length of the graph of y equals f of x over ab, we start by dividing ab into n equal subintervals. So x naught is equal to a, and then xi is equal to a plus I delta x, where delta x is b minus a over n. This is the same kind of thing that we did for approximating definite integrals. We're taking our interval ab and we're breaking it into subintervals of equal distance, delta x. Then the length of the ith segment, the segment over the interval xi minus 1 to xi, is given by the distance formula. And remember, this is x2 minus x1 squared and y2 minus y1 squared. So our x2 and x1 are xi and xi minus 1. So we have xi minus 1 quantity squared, plus, now our y values are given by the function values because this curve is y equals f of x. So we have f of xi minus f of xi minus 1. And this is the length of the ith segment. Now let's do a little math on this so that we can simplify it. Now notice xi minus 1, this is the width of a subinterval. So this is delta x. And here we want to use the mean value theorem to replace the f of xi minus f of xi minus 1 with an expression that's going to be more convenient for us to move forward with our computation. So recall, the mean value theorem says that for a function f of x that's continuous on the closed interval ab and differentiable on the open interval ab, there exists a c in the open interval ab such that f prime of c is equal to f of b minus f of a over b minus a. This is the slope of the secant line between the 2 points, and this is the slope of a tangent line at the particular point x equals c. So what we're saying is there's some c in this interval for which the tangent line at x equals c has the same slope as the secant line between these 2 points. That's the mean value theorem. And so if we multiply the b minus a on both sides, we have f of b minus f of a is equal to f prime of c times b minus a. So what we have up here is f of xi minus f of xi minus 1. And so we can replace that by f prime of some number in that interval multiplied by xi minus xi minus 1. Now remember, we started this by saying that f prime was continuous on the closed interval ab. Well, if f prime is continuous on the closed interval ab, then certainly f is continuous on the closed interval ab. And if f prime is continuous, then certainly it exists on the open interval ab. So f is definitely differentiable on ab. So we can apply the mean value theorem for the function that we were given. So we're saying that there exists a c in ab. So for our interval, we're going to call that number xi star, because it is between xi minus 1 and xi. And so we have f prime of xi star multiplied by xi minus 1. That's here. Again, this is the length of the linear segment over the ith interval. So now notice xi minus 1 is delta x. And so we can factor out a delta x squared from what's under the radical. And so the remaining factor is 1 plus f prime of xi star squared. And now this delta x quantity squared can come out of the radical because delta x is a positive value. And so we're here. So this is a simplified version of the length of the linear segment over the ith interval. So to find the length of the curve, we're going to sum up these lengths and then take the limit as n goes to infinity. And so the length of our curve is the limit as n goes to infinity, the summation of the SI, or the summation that we have here. And since f prime is continuous, we know this limit is going to be this definite integral. So we have the length of the curve, or arc length we call it, is the integral from a to b, radical 1 plus f prime of x squared. Similarly, if we have x is a function of y, x equals g of y with g prime continuous on the closed y interval from c to d, then we have the arc length there to be the integral from c to d, radical 1 plus g prime of y squared. So let's take a look at an example. Find the length of the curve where f of x is ln of cosine x, and x goes from 0 to pi over 3. Well, we know we're going to need f prime of x for our formula. So let's start by taking f prime of x. We do that by using the chain rule, and so we have 1 over cosine x multiplied by the derivative of cosine x. So we have negative sine x over cosine x, or negative tangent x. So we set up our integral. The arc length is the integral from 0 to pi over 3, radical 1 plus f prime squared. So we can simplify what's inside by making this 1 plus tan squared x. And we know that 1 plus tan squared x is equal to secant squared x. And now we would love to cancel the radical with the square here, but remember we have to check that secant x is positive over this interval. And in fact, it is. Remember, secant x is 1 over cosine x, and think about the cosine graph. The cosine graph is positive for 0 to pi over 3. So we know that this is in fact greater than or equal to 0. So we can simplify our integral now to the integral from 0 to pi over 3 of secant x. And so that's ln of absolute secant x plus tan x going from 0 to pi over 3. So we plug in our bounds. Secant of pi over 3 is equal to 2. Tangent of pi over 3 is equal to radical 3. Secant of 0 is 1, and tangent of 0 is 0. So simplifying, we have ln of 2 plus radical 3. I dropped the absolute value bars because I recognize that 2 plus radical 3 is a positive number. So we're here. And this is the arc length. This is the length of the curve over the interval 0 to pi over 3. Let's take a look at another example. Find the length of the curve for f of x equals x to the third over 6 plus 1 over 2x for the x values between 1 and 2. Again, we know we're going to need f prime, so let's take the derivative. We get 3x squared over 6, or 1 half x squared. Here we have 1 half x to the negative 1, so we have negative 1 half x to the negative 2. And so we can write this as x squared over 2 minus 1 over 2x squared. And so we set up our integral, and we're here. Now you might be wondering, what could I possibly do to integrate this? Well, let's see if we can get anywhere by multiplying this out and simplifying with the 1. So we square our x squared over 2 minus 1 over 2x squared. That's written over here. Notice when we do our inner and outer, the x squared factors cancel, and we're left with a negative 1/4 for both the inner and the outer here. And so we're here. And so this replaces the x squared over 2 minus 1 over 2x squared quantity square. So that's these three terms here. Now we already had a 1 in there, so let's combine the 1 and the negative 1/2. That gives us a positive 1/2. So now we're left with this under our radical. Now how does this compare to this? Now we have the same three terms, but we have a positive sign for the 1/2 instead of the negative sign. Notice that this negative 1/2 came from a negative here and a negative here. Now we have a positive 1/2, so we can factor this as x squared over 2 plus 1 over 2x squared, quantity squared. Because our inner and outer terms here are going to be positive 1/4. And so we're going to have positive, positive, and positive 1/2. So we can factor this here, and now notice that x squared over 2 plus 1 over 2x squared, that's always going to be greater than 0. So we can cancel the radical and the square, and now we're here. And now we can integrate. So we have x squared over 2 plus 1/2 x to the negative 2 that we're integrating. So we take the antiderivative, plug in our bounds, and subtract, and we get 17/12. So if you were first trying this problem on your own, you might not have recognized that what we have here could be factored. But now that it's being pointed out to you, hopefully you'll remember to look out for this with these types of problems. Let's take a look at another. Y squared is equal to 4x, and we're looking at the y interval from 0 to 2, and we want to find the arc length. So the first thing I notice here is that this is not y as a function of x. This should be written as x is equal to a function of y. So really, we want to solve for x here and write it as x equals a function of y. So here, x is equal to 1/4 y squared. And now you're using the arc length formula that integrates on y, because we have x is equal to a function of y. So take a couple minutes, please pause the video and work on that. For the arc length formula, we know we need g prime of y, so that's going to be 1/4 times 2y, or 1/2 y. And so that goes here. And so let's simplify what's under the radical and then continue. So we're going to have 1 plus 1/4 y squared under the radical. Now we're not going to be able to use a regular U substitution here, but we'd like to be able to use a trig substitution. And I think it would be convenient to get rid of the fraction inside the radical. So let's factor a 1/4 from under the radical. So we have radical 1/4 parentheses 4 plus y squared. And this 1/4 under the radical can be pulled outside of the radical as a factor of 1/2. So now we've got this 1/2 outside our integral, and now we have something that looks much easier to deal with. We have 4 plus y squared under the radical. And so let's let y equal to 2 tan theta. And then dy would be 2 secant square theta d theta. And so we have 1/2 on the outside, we have radical 4 plus, and now y squared is going to be 4 tan square theta. And dy is going to be 2 secant square theta d theta. And notice the bounds on our integral have changed as well now that we're in theta. If y is equal to 0, 0 is equal to 2 tan theta, that means tan theta must equal 0, and so theta is equal to 0 in that case. And then for y is equal to 2, 2 is equal to 2 tan theta, that means tan theta is equal to 1, and so theta must be pi over 4. So the bounds on our new integral are 0 and pi over 4. We can cancel the 1/2 and the 2. We could also factor a 4 from these terms under the radical, and so we're here. We'll pull out the radical 4 as a 2. The 1 plus tan square theta gets replaced by a secant square theta. And then we can simplify radical secant square theta to a secant theta on this interval, 0 to pi over 4. And so what we're left with is a secant to the third theta, d theta. And so for this we're going to use the secant reduction formula with n is equal to 3. And so that gives us, we still have our 2 on the outside. And so integral of secant to the third x dx, in this case we have theta and d theta. So that gives us 1/2 secant theta tan theta plus, again, 1/2 integral secant theta d theta. So we integrate here. We can cancel the 2 with both of these halves. And so we plug in our bounds and subtract, and we are left with radical 2 plus ln of radical 2 plus 1. Let's take a look at another. Find the circumference of the circle of radius r by doubling the arc length of the semicircle. Y is equal to radical r squared minus x squared for x values negative r to r. So this is the equation of the semicircle, and we're asked to find the circumference of the circle of radius r by doubling the arc length here. So we know for the arc length formula we're going to need y prime. So using the chain rule, we have that y prime is equal to 1/2 r squared minus x squared to the negative 1/2 multiplied by negative 2x. So simplifying here, the 1/2 and the 2 cancel, and so we have negative x over radical r squared minus x squared. And so this is our y prime, and we're going to plug that into our arc length formula. Now notice we're looking for circumference here, and that's going to be double the arc length of the semicircle. So I put in a 2 here so that we have the entire circumference of the circle. So now let's square here. That's going to get rid of the negative and the radical. We're going to have x squared over r squared minus x squared. Now if there's any hope of getting something we can integrate here, we're going to have to combine this into one fraction. So let's write this 1 as r squared minus x squared over r squared minus x squared. And so we have r squared minus x squared plus x squared over the common denominator r squared minus x squared. And notice in the numerator these cancel, and so we have radical r squared over r squared minus x squared. We know r is a radius and it's positive, so we can simplify the numerator as radical r squared. We can simplify that to r, and we can keep the radical just for the denominator. And so now we're here. Now remember r is a constant, so this is looking like an arc sine. So in order to get the 1 here that we would like for the arc sine, let's factor out an r squared from under the radical in the denominator. So factoring out the r squared, we have 1 minus x squared over r squared as the remaining factor. So we have radical r squared. R is positive, so we can pull that out of the radical as an r here. And so we have radical 1 minus x over r quantity squared. And so we notice our r's cancel here. And we want to use a u substitution to get this to be an arc sine integral. So u is equal to x over r, du is equal to 1 over r dx. So we put in a 1 over r, and then we multiply by an r on the outside as well. So now we have 2r integral du over radical 1 minus u squared, and we just want to change our bounds to be bounds on u. When x is equal to negative r, u is equal to negative 1. When x is equal to positive r, u is equal to positive 1. So now we're here. Integrating, we have 2r arc sine u going from negative 1 to 1. So that's 2r times arc sine 1 minus arc sine of negative 1. Arc sine of 1 is pi over 2. Arc sine of negative 1 is negative pi over 2. So simplifying, we have 2 pi r, the circumference of the circle of radius r. So here we've worked on a few problems that we could actually compute the integral for arc length. But notice that when you look at these formulas, if you take a function's derivative, square it, add 1, and put it under a radical, For most functions, this is not going to be something that we could integrate. So keep in mind that it's common to also ask questions just to set up the integral for arc length. And this concludes our lesson on arc length.